Hello friends, in this video I will discuss a colligative property whose name is depression in freezing point. Freezing point. So it is a temperature at which solid and liquid phases of a substance are in equilibrium at 1 atmospheric pressure. Freezing point or melting point are almost same things, or for any substance, freezing point and melting point both have same value. For example, in case of the compound H2O, you know this compound H2O, dihydrogen oxide or hydrogen oxide. The liquid state of this compound is known as water, and the solid state of this compound is called as ice. So these two forms or phases of H2O can coexist, can be in equilibrium at 0 degrees Celsius at 1 atmospheric pressure. So let's say this ice, then we have here water, and temperature is 0 degrees C, pressure is 1 atmospheric pressure. So 0 degrees Celsius is known as the melting point of ice, and 0 degrees C is known as the freezing point of water. So what is there in water? The H2O molecules are present randomly. There is a very less order in between H2O molecules, or H2O molecules are present randomly in liquid state. So when we decrease the temperature, the molecules come closer, their randomness decreases, they approach towards a state in which their motion is least, means they have only vibratory motion and the translatory motion becomes zero, and that state is known as ice, in which water molecules are localized. They have very less randomness in the form of vibratory motion. So in order to bring the H2O molecules together, or in order to bring orderness between the molecules, H2O molecules, some energy is taken out and temperature decreases. So when we are moving from this water to ice statement, means when we are freezing water, temperature decreases, right? And when temperature decreases, vapor pressure also decreases, and at 0 degrees C, vapor pressure of ice and water is equal. Their chemical potential is equal. Their escaping tendency is equal. It is very, very important. So at equilibrium, this we can say mu solid is equal to mu liquid. Solid means ice, liquid means water. Chemical potential is equal, and this temperature in case of water, which is 0 degrees Celsius, is known as the freezing point. Now our topic is depression in freezing point. Now to water, if we add some solute whose molecules are very big as compared to the molecules of water. For example, if we add say sucrose or glucose or fructose or any other compound, let's say your glucose C6H12, now it is a very big molecule as compared to water molecules, and these big molecules when present here, if you see present water, in between water, what they do? They create more randomness, and when we want to freeze this solution, right, the freezing point is less as compared to pure water, because we have to take more energy from the system. We have to say given out more energy from the system in order to create order in the system or in order to solidify the system. Means always the solution of a liquid freezes at lower temperature as compared to the freezing temperature of the pure solvent or the pure solvent. And this thing can be represented graphically when we plot graph between the vapor pressure and temperature of pure solvent then solution. First, let's plot a graph between the vapor pressure of pure solvent and temperature. So the pattern obtained is very simple. Let's see please. Now suppose we have water at room temperature. Here, this is the room temperature. Temperature is taken Kelvin, and vapor pressure is there, vapor pressure of the water. Pressure of vapors of water at equilibrium is known as the vapor pressure. So this is, let's say, room temperature 298 Kelvin. If we decrease the temperature of the water to a liquid state, vapor pressure decreases and ultimately this water freezes at a particular temperature. So it is the, let's say, T naught. Okay, T naught means freezing temperature or freezing point of pure solvent. So it is the temperature at which here we get ice also. At this point, solidification of H2O starts, and at this point ice as well as H2O liquid coexist. These two phases are in equilibrium at 1 atmospheric pressure, and this temperature is taken as the freezing point or freezing temperature of H2O liquid, which is known as water. Further, if we cool ice, then the graph obtained is like this. Means the vapor pressure of ice is very low. So when we say heat ice, what? Below 0 degrees Celsius, ice directly changes into vapors. So there is equilibrium between this solid and vapors here below 0 degrees Celsius, and vapors are formed in very less amount. That is why the vapor pressure here is very less. So this is your solvent in liquid state, water, and here we have the ice or solid solvent. Ice means solid solvent. Now let's take a solution of glucose in water and measure its vapor pressure at room temperature. We are here. We are here. The vapor pressure of a solution is always less at a given temperature as compared to pure solvent. What I am saying, vapor pressure of a solution is always less as compared to its solvent at any given temperature, because from solution less vapors of the solvent is formed because of decreasing surface area. Some surface area of solvent in solution is covered by the solute molecules, which are non-volatile. Solute molecules don't form vapors. And if you decrease the temperature slowly and gradually and measure the vapor pressure, we get a curve like this. This is the curve obtained in case of solution. And ultimately your solution freezes at this temperature, and this is the T, the freezing temperature of solution, which is always less as compared to freezing point of pure solvent. And the two differences, that is T0 minus T less is T is always less as compared to T0. The freezing point of solution is always less. Is equal to delta TF is known as the depression or decrease in freezing point of the solvent or liquid when some non-volatile compound is added to it. So delta TF is known as the depression in freezing point or decrease in freezing point. So this delta TF is proportional to amount of solute in solution. More is the amount, more is the value of delta TF. And the amount of solute is expressed in terms of molality. Delta TF is proportional to M. Small m means molality of the given solution, and molality is equal to the number of mole of solute present in 1000 gram of solvent. M, the molality of solution, which is independent of temperature. Molality is independent of temperature because here we are considering weights of solute as well as solvent. We are not considering volume, right? So that is why on changing temperature, volume changes, but amounts of both substances don't change. That is why molality remains unchanged on changing temperature. So delta TF is equal to, that is Kf into M. This is very important. And if we have any substance whose molecular mass is M, its W 2 gram is dissolved in W 1 gram of the solvent, then M, the molality is equal to W 2 over M into 1000 over W 1. This is the definition of molality. What is this? This is the number of mole of solute present in this much weight of solvent, and this is the number of mole of solute present in 1000 gram solvent, and it is the molality of the solution. Now put this value of M in this formula, then delta TF is equal to Kf into W2 into 1000 over M into W1. This formula is very useful. With the help of this formula, we can calculate the molecular mass of any unknown compound. So before discussing a numerical, let's define your Kf, known as the mole depression constant or cryoscopic constant. Here in this equation, if m is 1, then this Kf is equal to delta Tf. From this equation, if solution is 1 molar, you see please, this is the formula. In this formula, m is 1, then Kf is equal to delta Tf. So the molar depression constant is equal to the depression in freezing point when the solution is 1 molar. When the solution is 1 molar. For example, if we take 1000 gram water, and to this we add, let's say, glucose C6H12O6. It is your 180 gram, right? And the freezing point of this solution will be, that's a minus 1.86 degrees Celsius. A minus means there is a decrease from 0 to minus 1.86, and 1.86 is the value of Kf, the molar depression constant for water, and it is the property of solvent. For water, Kf is always 1.86 irrespective of nature of the solute. If we add 1 mole of any other substance, let's say sucrose, urea or fructose, etc., then the depression in freezing point is always 1.86. Right? This is minus means freezing point and depression is 1.86. The difference of the two values. Depression is positive and the freezing point solution of any compound in water is always negative. It is always less than 0. It is less than 0 means it is always negative. Okay, let's calculate the depression in freezing point of this your water when we add glycol to it. And glycol is added in water in order to decrease its freezing point, so that it does not freeze at 0 degree Celsius. So what we do? We add 550 gram of glycol compound हमारे पास है. This is the compound CH2OH, molecular mass is 62. It's 550 gram is dissolved in 1000 gram of water. So our aim is to calculate delta Tf, the depression in freezing point, is equal to Kf 1.86 is always for water, and W2 is 550 into 1000. Okay, then what we do? We have this 62 and 1000 gram solvent. We are dissolving 550 gram of CH2OH in 1000 gram water. What is the value of depression in freezing point? Okay, please. This comes out to be your 16.5. Let's say this is the value of delta Tf. Difference, it may be in degree Celsius or it may be in Kelvin. Means the freezing point of this solution of your glycol in water is less by this number as compared to freezing point of water. Freezing point of water is 0 degree Celsius. It means the freezing point of this solution is minus 16.5 degrees Celsius. Minus. So it is a very, very less temperature. So that is why we use your solution of glycol in water in radiators, etc., in hilly areas, so that water or other liquids which you are using don't freeze in vehicles or in other apparatus which we are using at low temperature. And it is a very, very big use. In order to melt ice in hilly area, what we do? We add sodium chloride or calcium chloride to it. Means ice easily melts or its freezing point decreases from let's say minus 15 to up to minus 50 also, minus 50. Actually, the melting point of ice, right, which is 0 degrees C in pure ice, it decreases when we add some other salt to it. Mostly we add the sodium chloride or calcium chloride. Okay, please. Thanks. Namaskar.